So in 5.2, what we're going to do is we're going to continue the idea of energy. So last class we talked about work and energy, and I was giving you examples. If I push on a garbage can, let it go, I do work on the garbage can, positive, to increase the energy of the garbage can, and then it slows down as friction stops it, as it comes to rest, so it loses energy of friction. In the end, the net work done will be zero for it to stop. It's going to gain energy and then lose that amount of energy to stop. And in this chapter, we're going to start talking about conservation as well, and the idea of energy neither being created or destroyed, and how it can be just changed in its form. So we're going to take a look at three specific things here: the different forms of energy, the word kinetic energy theorem, and then we're going to look at problems that involve potential and kinetic energy. So let's start with this. So what does kinetic mean to you? What does kinetic mean to you? Here?
In motion.
In motion, exactly. And we see that it says the object's motion right there. Very good. But if you remember from this static and the kinetic coefficient of friction, kinetic had to do with when it was in motion. So our formula is 1/2 mv squared. V represents what?
Velocity.
Velocity, because it's talking about motion, right? Use the context, so big volume here. Because we're going to have volume at the end of the year, not to be confused with this V. That's a capital V volume. And it's mass, obviously. Our measurement of energy is still joules, which is really kind of interesting to think about. What was our last formula that came out to be joules? What was the formula? Newtons times meters. So the last formula was this, right? Now, cosine theta has no units. This was a Newton, this was a meter, and this became a joule. And now suddenly we have a kilogram and a meter per second, that quantity squared, and that is a joule. It's interesting to think about now, right? Yet somehow these different forms come out to be the same actual thing because they're both energy, they're both the same concept or idea. And if you break this down, what Newton is kilogram meter per second squared, so kilogram meter second squared, kilogram meter second squared. Okay, so it's the exact same unit really, just a completely different form of that. And it's really kind of interesting to think about that. Okay, the way these units end up working out for different types of energy. So let's take a look at an example. Should we read for us, please?
Yeah, sure. A 12 kilogram bowling ball moves at 3 meters per second. How fast must a 4.5 gram bouncy ball travel for it to have the same kinetic energy as the ball?
So let's think about this in logic first. 12-pound bowling ball, 3 meters per second. So this is like that quick, a little bit quicker than that. And that's like 3 meters, and I was trying to get there in a second. So that's how fast it's going. Now we've got, you know, those little bouncy balls, or like the little super balls? You can bounce them, and they go really high, and they retain their energy. 4.5 grams compared to 12 kilograms. So first thing we have to think about here, I don't think so, but there are paper towels, but you could just go get a tissue, or maybe next door, check in the other room for a box of tissues. Or even in the math science office, right there on top of the fridge there's a box of tissues. There should be. Okay, so we have to think about our base units here. And we're still looking at kilogram as our base unit. Again, we're looking at kilogram, which is really a little bit different than what we're used to because we have a prefix there. So the 4.5 grams, what do we have to do to that? How do we change that? What does that become? Katie? Do we multiply it by 1,000? Well, let's see. It's in grams. Yeah, I think we divide it by 1,000 because this is how we're going to convert. Right? Isn't that what the conversion factor is? So let's use our conversion factor for that one. The first mass was 12 kilograms. A lot of these problems are going to involve more than one mass, so we have to start using subscripts when applicable. Okay? And some textbooks will use lowercase m for one mass and capital M for the other mass. And respectively, the capital M will be the larger mass, always. So this turns out to be, we move it, 3 decimal spots, right? 0.0045 kilograms. All right, we know the velocity of the first bowling ball. That velocity, we'll put it up here. V1 is 3 meters per second. It's not a final, it's not an initial. It's a velocity at an instant in time. This is not a final, an initial, an average, any of that. Ready? I bowl the bowling ball. And somehow along the lanes, I set up just 2 little lasers, and they measure the distance, they measure the exact time it takes, they can get the average velocity. Or I set up 2 lasers right next to each other at a really small distance. And if I can measure the time it takes to get from here to here, I'm getting that velocity at that instant in time. It's called the instantaneous velocity. It's part of what calculus is about and how it applies to physics. So here, we're looking at the instantaneous velocity of that object at that moment. So our goal is to figure out what velocity should a Super Ball have at some instant in time to have the same amount of energy. So what should I do? How would I approach this? You guys should be able to solve something like this by now. I've given you equations. The problems are not more difficult than what we've done in the past. We have the mass and the velocity of one. We only have the mass of the second. We're trying to figure out how fast should the bouncy ball go. How could I do that if they have the same amount of kinetic energy? The same amount. Yeah?
You find out how much kinetic energy the bowling ball has, then you plug that in for the equation for the bouncy ball.
So you're saying take the kinetic energy of the first object and set it equal to?
The kinetic energy of the second object.
Yeah. Okay, that's how you would say that in the formula. That's exactly what he said. You find the kinetic energy of the bowling ball, set it equal to that of the bouncy ball, solve for V. That's what this is. So you've got 1/2 m1 v1 squared. I'm going to do it in formula. It makes sense, right? You could find a number and then do it. But why not use formulas so that we have some sort of generic solution we could apply later? Okay, the object is the first one and the second one. So what do you notice? What don't you really need for this problem? You could drop off what? What cancels?
1/2.
Yeah, right? We all understand that, right? Multiply both sides by 2. And on both sides, the 1/2 drops off. That's gone, that's gone. Whenever you have a factor on both sides, it's gone. Now, M1 and V1 are different than M2 and V2, or it's going to have to cancel. But at this point, what are we solving for? What variable are we trying to figure out? That? V2. So, to clean it up a little bit, this is what I have right now. And I want V2. So, give me V2. What do we have? How do I isolate V2? It's a 2-step process here. You have to get rid of the multiplier in front of it, and you have to get rid of the actual power. Ellie, take us through it.
Divide it
By?
V1 or V2.
You're trying to get V2 by itself, so you don't want to move it. Move what's next to V2.
And
What's next? Here's V2 right here.
okay, sorry.
That's all right.
Divided by M2.
Good, very good.
And then do we have to get rid of the exponent?
Yeah, so how do you get rid of a square? Take the... If you get rid of a square, take the square...
Root.
There it is. So you take the square root of this side, it gets rid of that square right there. Okay, so you divide by m2 on both sides, then get rid of the square by taking the square root. So here's your answer for v2. Everything's gone. I've crossed it off. Okay, I got rid of it. You divide by m2, and I get rid of the square by taking the square root. So this is your solution, your generic. So m1 you can plug in, that's the mass of the bowling ball, 12, times 3 squared all over 0.0045. Take the square root of that answer. That'll give you v2, the velocity the bouncy ball should be. Again, a generic solution. What could you have done? Oops. What could you have done? What could you have done instead of finding a generic solution? Katie? Yeah, you could have plugged in up here maybe if you wanted to. Just plug in for all of them and then solve for the missing variable. Okay, you could have plugged in. That would have given you, I'll put it over here, 12 times 3 squared equals 0.0045 times v2 squared. Okay, you could have plugged in there, and then that would have given you that. If you want to solve that way, that works also. It's just all numbers then, right? You got to do 9 times 12, well that's right here, 9 times 12. And then you got to divide by this, well that's right here, divide by this. And then you got to take the square root, so that's right here. So in the end, the generic is the same thing as the actual plugging in. Okay, there's V2. Yeah.
So, to get rid of the,
To get rid of a power, you take the root of that power.
yeah.
So if it's the third power, you take the third root. Remember that thing with the little 3 here?
Yeah, so when you did to the other side, you need to take away.
Yeah, so I square rooted both sides technically. So here, sorry, I didn't show it. You take the square root of both sides, right?
So why is the square root still there?
Well, because this square root here and this square cancel out, right? Those reduce.
Yeah.
And this square root I took on this side. There is no square over here. This one you mean right here?
Yeah.
Well, if I wanted to, I could individually cancel this, but this would still have a square root around it, and so would this. So if I did what you're saying, Nat, here's what it would look like. That's fine, you could do that. You would write it like this as your answer. Okay? You could drop the square root on V1, because the square root and the square on V1, those cancel each other out. Okay, this, remember, M2 is not here. We already got rid of M2.
Okay.
Does that make it more clear, I guess?
I was thinking.
Yeah, no, not the whole thing. This is gone. We divided by it. So we're just square root square cancel.
Okay,
Yeah, if you have it, the whole thing, you can cancel individually, but the other part needs to keep it still.
Okay.
So you can write it that way also. What do you get as a number? Ellie, what do you get?
154.92.
That works. 154.9. Others agree or disagree? Yeah? Okay. I'm seeing nods. Sounds good. All right, so let's take this idea now of kinetic energy, the fundamental type of energy of motion, and relate it to work. So, we're going to go through what's called a little quick derivation of this to show you where the formula comes from. But think about it for a second. Let's go back to the trash can example. I want you to think about this and come up with the work kinetic energy theorem. What are you going to look up? So take the garbage can. Right now, how much energy does it have? How many joules? 0. I start to push it, right? And I release. And it has some velocity. Okay, so I go like this, and it has some velocity when I release right here. And then at the end, what's the velocity?
0.
So, from here to here, what changed? The object's what? Now that we're looking at today's lesson. The object's blank changed. Kinetic energy. It went from some quantity, because it had velocity and mass, to 0 because it had no velocity, yet still had mass. So it's kinetic energy change, delta, kinetic energy change, right? Think about delta, kinetic energy. What caused it to change? Specifically, from section 5.1, the what done by friction? What's the word?
Force.
Not force, you're close though.
Work.
The work done by friction. The force is what slows it down, absolutely, but what changed the kinetic energy was the work done by friction. Think about it. Where did the kinetic energy go? We can't just not go anywhere. So the kinetic energy that it lost from here to here had to go somewhere. It went into the work. There was a balance there. The work done by friction is what killed the kinetic energy of the object. So we're going to see that there's a work-kinetic energy relationship here. Does that make sense? Okay, it has to go somewhere. The energy can't just stop. You can't just lose energy to nothing. It has to be lost somewhere. And that somewhere is like a thermal loss or some sort of frictional loss. It's always what that is. It's always going to be a frictional loss. Whether it's air resistance, it's still friction, right? Something that's resistive, a resistive force. Okay, so what we're going to do is we're going to start first with our definition of work. Now we're looking in one dimension, and what I mean is that assume that theta is going to be 0, right? One dimension is this, left to right. So if the object is only in one dimension, the force is only in one dimension, the direction is only one dimension. So we'll start with this first. But we can assume that theta is equal to 0 degrees because the force acts in one dimension, like that, on top of the directional. So this quickly becomes just FD. Why is that? What's the cosine of 0? 1. Okay, and some of these things you might memorize after a little while. You will memorize them eventually in your Algebra 2 trig, so it doesn't hurt to think about it. Okay, then what we're going to do, we're going to think about what is really the net force on an object defined as. What is F really? What can you always substitute the net force? Because remember, if we're looking at net work really, right? This is like we can put this as net work. We talked about how this is then the net force. We did this last class at the very end of the last example. MA. So we can write W net or just W. I can drop the net. I don't really need it, but I want you to see that. This is really MA. Look how mad I am. So,
Why is it 0 degrees instead of 180 degrees?
because what I'm saying is that the motion is to the right and so is the actual force is to the right. So maybe just cross this off if it helps. One dimensional. They're both the same. It could be 180 and this whole thing would be the same, except what kind of sign would you have? a negative sign, because cosine 180 is -1. And when you do have frictional loss, you'll see that the work done will be negative, and we'll see where that comes into play. Okay? So you could, if you wanted to call it 180, you could, and that would be when friction is being applied. I'm talking about an applied force. Either way it could work. So right now I have m times a times d. Okay, m times a times d. Now, think back and write a little side note over here, please. Put a little box on the side. Remember this formula? Vf squared equals vi squared plus 2ax. We learned this formula in the very beginning of the year. Now, what does x represent in this formula again? Who remembers? What was x in this formula specifically?
Distance.
Displacement. But yeah, like distance. Some change in position, right? Now, Alejandro, it's fine that you said that because I'm going to make the assumption, ready? If I start here and end here, my displacement and distance are the same. That's why, Klaus, you are only going in one direction also. Start here, you've got to only go in one direction. Because if I turn around, now displacement and distance are different, and I can't make the substitution. So I'm going to assume one-dimensional positive motion, I should have said, really, right? Only positive, not just one dimension. So AX can really become AD. I could write this as a D because displacement and distance are the same if I only travel from point A in a straight line to point B. They're the exact same thing. Now what I'm going to do is, I'm going to see here, look where I'm going to point. I have AD in this formula right here. So if I could isolate AD with some sort of a generic formula, I can substitute it for AD right here. So I'm going to start by rewriting this because of the associative law of multiplication. Oh, look at that. You're finally using those laws, right? Move the parentheses over and group AD together in your mind. And then you can substitute for AD if you solve for it in red. Let's solve for AD. Alejandro, help me out because you were the one who started this one. How do I get rid of stuff? I want to get AD by itself in the end, right here.
Divided by. Wait, you're talking about the red?
Yeah, in red, I want to get AD by itself. I'm boxing it in, see?
Okay, well, you could subtract it.
Subtract what?
2AD from. Actually, no. Divided by 2.
Okay, but before I divide it by 2, get rid of the VI squared.
You subtract it to the other side.
Yeah, very good. And then, go ahead.
And then you would divide it by 2.
Very good. Okay, so you subtract VI squared. Remember what I taught you guys at the beginning of the year. If VI were a number, how would you get rid of it, right? Treat everything like it's a number except for the quantity AD. Because AD is what you're trying to solve for. So if VI were a number, and it was like a 5 here, you would subtract it, so subtract VI squared, really, and then divide by 2, because 2 is a number, it's a multiplier, it's a factor. So that's what AD is. So let's substitute that expression right here in for AD right here. And what you're doing is like, it's called the derivation. It's where you derive or show where the formula comes from, or the relationship, or the theorem, or whatever it may be. Does anybody recognize stuff here? There should be a lot of similarity. Look at this formula. Look at it. Intently look at it. Don't just look at it quickly and glance, but look at the actual structure of it. There's some similarity. Try to figure out that similarity. Similar to another formula, or pieces of other formulas. Frank?
The VF minus the VI squared is, I just can't think of the formula.
There's a few formulas with VF minus VI for sure. Theo?
They all have mass.
Okay, mass, if you distribute, it goes to both. Very good, Theo. So do that first. Right, if I distribute the mass and distribute the 2, a 2 in the denominator, and I'm pointing here, ready? Look. This 2, remember, divides into this, and it divides into this. A monomial always divides into every term of a numerator. And there's 2 terms here. So they both get 2's. The m gets distributed. So again, you're distributing the m to both, and then you're also dividing both of these by 2. Come on, look at it. What is it, Ellie? No. Ugh. Come on.
Got the constant sheets off.
What does this not look, or what does this look familiar to? Seriously, guys? please, somebody get it. Help me out here. If you're, when you see it, you're like, oh my gosh, it's identical. It's just, it looks like a little misrepresented because it's over 2. Theo?
Wait, 1 second. Hold on. Velocity.
No, there is velocity in it. Come on.
It looks like the.
All right, I'm giving you the last and final step. Cop-outs. Come on, people. All right, here we go. This is what this one really is. And that's what this really is, right?
Yeah, that's what I said. It looks like
Now let's see if people could see it. Come on, really? Think about the garbage can. Think about the name of this theorem. Scroll back up. What's the name of the theorem?
it looks like this.
What's the name of the theorem?
Wait.
Seriously.
I'm scrolling.
It looks like the first formulas that we get. Is that right?
Emma. Emma, what is it, Emma? Kinetic energy. Look, this is kinetic energy final.
That's close.
This is kinetic energy initial. All right, we just put her in the formula.
Right there. Oh.
Okay.
I thought you did a long time ago.
Look at my.
Oh, I meant like, you know, that 3 minutes ago I meant, sorry. My fault. I meant like 3 minutes ago. So look, that's what it is. 1/2 mv squared is kinetic energy. If I put an F, it just means final kinetic. This means initial. What does final minus initial mean? Final minus initial, what's another way of representing that? With what symbol?
Delta.
Delta, change. That's why it's the word kinetic energy theorem. I was talking earlier about the change in kinetic energy. The change in kinetic energy of an object is equal to the work done on the object. This is assuming there's no potential energy involved. If there is, we'll talk about conservation later. But right now, this is the word kinetic energy theorem. Here we go again. Now let's see if it clicks. The garbage can has no energy. I push it. It starts to move. That's VI. What's VF?
0.
So this is going to drop off right here because this is 0. So the amount of energy that I had initially, it's all lost where? To the work done, to FD. You can replace that work done there, and you don't necessarily have to write it this way, but you can. This is the way the theorem is written as it is now. But you could write it like the following. You could write it as F times D. Put cosine theta in there anyway. Equals delta K E. Okay, so you could use that. Instead over here, you could put back to your 1/2 mvf squared minus 1/2 mvi squared if the object's moving, and then it just slows down. Okay, so when substituting, you're going to do this again, but the theorem is what's boxed in. That's what you're going to start with always. And then you're going to substitute. So if you want to, one sec, Kate, I see you. If you want to write it like this, you can. But on your formula sheet, it's not going to be written like this. It's going to be written in a very simple form, what you see boxed in at the top. Okay? So that's what's going to be written, but this is really what it means. The work done equals the change in kinetic energy. Kate?
Wouldn't the change in kinetic energy just be 0?
No, I mean, ready, watch. Remember, it's from the instant I've already released it, not from when it's before it started. Yeah, from before it started to when it ended, the overall change is definitely 0, because energy can't be created or destroyed. But I give it energy, and then it loses energy to get back to 0. That's how it works. So we're looking at the process involved, not necessarily from before it started to after. Okay? So let's go ahead and take a look at an example of this. Here's your bone. On a wood floor, you decide to slide around when you've just put on a new pair of socks, and we all know what that's like, right? Let's be honest. It's awesome. New socks, you slide everywhere, and tiles even another story. It's crazy. So you run and start to slide with an initial speed of 2 meters per second. So you're literally ready, you're running, and then you like kind of start gliding. Do you know what I mean?
Yeah.
Everybody knows what I'm saying, right?
Yeah.
Okay. Almost like a ski stop or a skate stop, but you're not stopping because there's no friction, or very little. So you run, start to slide with that speed. How far will you move if the coefficient of kinetic friction between your socks and the floor is 0.1? 0.1. Now, you might say, oh my gosh, I don't even know how much I weigh. It's independent of the mass. Notice, is the mass in the problem anywhere? So you think you need the mass? So what's going to happen somewhere along the way? Mass will cancel out. Okay? Let's prove that, all right? So we can go back to our work kinetic energy theorem, because it's moving initially, and then it stops, and it loses energy due to friction. That was the garbage can. This is exactly the same thing. These are the same exact problems. They're identical. Okay? So we've got work equals change in kinetic energy. I can write down my stuff over here. VI is 2 meters per second. VF is 0 meters per second. Mu K is 0.1. That's it. That's all you know. Seems impossible to think about how you could solve this, but you can. So work equals what? Work equals what? Work equals what? Katie?
Or 2B.
No. Work?
Work equals final minus initial.
Oh.
Okay, so how do I write that?
0 minus
Yeah.
What?
She just said
0
it.
minus 2. Right?
0 minus 2.
Okay. You're doing the final.
Yeah, but give me the formula to plug in. That's all I'm asking.
Sorry.
It's all right. It's all right. Give me the formula. Class?
Is it KDF minus KDI?
Good. So final minus initial. We just wrote this, right? I'm just reiterating it so we all know. Nat?
1/2 or MVF2
Squared.
squared minus 1/2 MVI squared.
So final minus initial. What about the work? The formula for work we know is force times distance times cosine theta. What's theta in this problem? What's doing the... No, be careful now. I know, you think it's 0. What's doing the work? No, what's doing the work on this object to cause it to stop? Friction is doing the work. Not you. You started sliding, you gave yourself kinetic energy, you're done. Friction is doing all the work to slow you down. Friction has an angle of what? With your motion, friction is which way?
180.
Yeah, 180. Which means this side's going to be negative. Oh, well, no problem, because this is going to be 0 minus something. It's also going to be negative. Okay? So this is going to be, again, theta equaling 180. Again, because this force is really FF, the force of friction. Please write that here. This is FF, the force of friction. You always want to identify the force you're using or looking at. In this case, friction. What's the formula for friction? This is why these aren't going to go away. You need to memorize these. I mean, not memorize, but know them, be familiar. Next.
K times Fn.
Yep.
Which is like energy.
We'll get to that in a moment, which it is, you're right. And we still have cosine of theta here. Can I do this for now? Is that safe to say? We could just cross that off? Because VF is 0, it's not worth carrying me down anymore, it just really isn't. Now that we already said, well, Fn, that's just mg, isn't it? How do we know that Fn is mg? Yeah?
Is there no extra vertical forces acting?
Very good. The only vertical forces that are acting are the normal force and the weight. Take a look at my free body diagram I just drew at the top. The weight is pulling down, that's Fg. The normal force is pushing up, that's Fn. There's no acceleration vertically, I'm sliding horizontally, right? So there's no vertical acceleration. So the sum of the forces in the y direction should equal 0. So really you have Fn minus Fg equals 0, and you should know this by now that for these problems, Fn, you move the Fg over, Fn is equal to Fg, which is why Natalie said Fn would just be mg. Okay, if I have to write that, I will, but I want you to see that you don't really need to write this every time anymore. There's your free body diagram. Here's what I'm saying. Sum of the forces in the y equals ma. You have Fn acting up minus Fg acting down. That equals 0 because there's no acceleration here. So Fn is equal to Fg if I add it over, but Fg is really mg. So Fn is really mg. So I'm going to put an mg over here. In for Fn. Put an mg there, put your mu k back in front. Put d right after that. I can't make the mu, it's too close. There we go. Now this is just going to equal negative 1/2 mvi squared. Remember, we dropped this off. This is gone. Do not copy this down again, please. This is gone. Final velocity is 0, so we drop it off. So we're just left with this piece carrying the negative. Where is this negative going to cancel again? Take a look here where I'm pointing. How is this negative going to go away? How is it going to cancel? Where? Klaus?
You put it on the other side.
Yeah, but what's it going to cancel with eventually?
Cosine of 180.
Cosine of 180 is negative 1. And this is going to be a 180 we're going to plug in, so that's what I meant. But yeah, once you have the -1 here and the negative here, you can put it on the other side and they become positive. What's on both sides of the equation? What's on both sides of the equation? And this whole equation is multiplying. So everything is factors now. So anything that's on both sides can be canceled.
Oh,
Everything's factors. Go ahead, Allie, it's fine.
math.
Mass. Good, you had a little revelation, that's good. See that, right? It's like, oh my gosh, that cancels. It's pretty amazing. Now, why this is so amazing, I think, is that it doesn't matter what size you are if you do this. You have the same initial velocity, you should travel the same distance if you're on the same form. So if you want to, for the extra credit, what I'm going to ask you to do is to do this, actually. But if you want to do it with somebody else, it'd be really cool. Somebody that's not the same size as you. Okay, so maybe a friend of yours that might be like 10, 15 pounds heavier, try it out. Try to wear like the same socks. It might be kind of gross, but or just have the same pair at least. Maybe 2 pairs, but the same exact type. Buy new socks. And if you run with the same speed, and it's hard to do, obviously, but try to run with the same speed and start going at the same exact time, so do it in tandem, you should slide the same distance. Because the answer is independent of mass. Okay? It's a lot of parameters that could go wrong, though, obviously, right? If you don't both have the same initial velocity, it doesn't work. If you wear different socks, mu k is different. So D is dependent on all, like solve for D in this formula. We'll see that it's dependent on all those things, yeah.
So for the extra credit, we have to find a wood floor.
Yeah, so you need it, or tile. Tile works too. So tile or wooden floor, but you have to have just socks on. So this is from risky business, I was telling you. Tile Cruz comes in with a guitar.
Extra credit if we dress up.
Yeah, no boxers, please. Wear full clothes. I'll allow you to come in with a guitar doing that. That'd be awesome if you want to.
Okay, me and my
You have to
brother.
film it like all your extra credits.
Joking.
Where have you not known? There's been like 5 extra credit. No, 4.
Have there?
3, 4,
Three.
3.
Like two.
3.
No,
I think this would be number 4. There have been 3 opportunities for
I
it.
thought there were two, the scale one and the shadow one with the highlight.
It's a scale and shadow, that's it?
Yeah, there's only two.
Yeah.
All right, fair enough, too. Well, I mean, that's 8 per year, 2 per quarter. That's not bad. If you do these and you do them properly, they give you like a point or 2 on your test, which is on the raw score. It'll affect your average a little bit. Maybe if you need that like half a point on the average to bump you up to the next number, it probably would. Anyhow, so obviously what I want you to do is in the problem, measure your distance afterward. Okay, see how far you end up going. That's what I want to see. So it's hard to figure out the other parameters, but let's go ahead and solve for D. If I wanted to solve for D, ready? I could get rid of this cosine of theta, because this is really cosine of 180, and I'm going to put a -1 there. Everybody see that? I'm going to put a -1 where the cosine theta was, because that's really cosine 180. It's the one thing I'm going to plug in. I'm doing that so that I can cancel these negatives. So the negatives are gone now. Okay, the negatives are gone. Cross them both off. So this -1 is gone, and it cancels this negative right here in the front. So that's gone completely. So we've got mu k times g times d equals 1/2 vi squared. So I want to divide by mu k and g. So I've got the 1/2 vi squared over mu k g. Let me show you that again. Okay, take this mu k, ready? This mu k here, this g right here, and divide by them. So divide both sides by mu k and g. Cancel, cancel. Divide this whole thing by mu k g. Okay, so this is what your solution turns out to be, but instead of putting a 1/2 in the numerator, just put the 2 in the denominator, right? So you could write this instead like this. Has the same effect on the answer. I would actually prefer it written the second way. Right? Take vi squared and divide it by 2 mu kg. That's what the same thing as multiplying by 1/2 is the same thing as dividing by 2. You should all know that one by now, right? Multiply by the reciprocal is the same thing as division. So this is your solution, your generic solution for D. So it turns out that the distance you slide is a function of your velocity you start with. So that has to be the same if you're going to do this with somebody else. The mu k, so the socks have to be the same. And G, you have to both be on Earth, which I hope you both are on Earth. So we'll be pretty good if we do this together. Okay, so get a running start and try and do it together and see how it works. What do you get for D when you plug in?
Oh wait, wow.
What do you get for D when you plug in? In my notes I wrote 0.0 meters. Clearly that's a typo. What's
I got
that?
2.04.
There. 2 point what?
04.
So I probably meant to put 2.0 meters. All right, 2.04. Can others just verify, please? Yeah? You know what's pretty interesting to look at? We have velocity squared, mu, which is unitless, g, which is meters per second squared, and somehow it turns out to be just meters. Okay, and it does work if you check it. You have meters squared per second squared over meters per second squared. The second squared cancel, meter squared over meter becomes simply meter. Let's see if I want to start the next one. I do want to start the next thing. All right. So for potential energy, the next part of this, we already looked at kinetic energy. Now we're going to look at potential energy. And for potential energy, we want to consider the fact that it has the potential to fall. The object could potentially gain energy. I couldn't say that word. Where did I put my stylus? Anyone see an orange stylus? An orange stylus? I left it somewhere in the room last period. I just don't know where.
Somebody definitely took it.
No, I moved it somewhere probably. It's in my pocket. Sometimes I do that.
Well, we should have our investigation.
No. All right. So, anyway, we're going to specifically talk about gravitational potential energy. So think about an object sitting on the edge of something, and an object sitting on the edge of even this little piece of cardboard paper. Okay, it's sitting on the edge here. It has energy due to gravity. Gravity wants it to do what? Yeah, gravity always wants you to go down. The table pushes you back up.
Okay, yeah.
So if I were to move this off the edge of here, the energy it has in its gravitational potential energy, when it falls, converts to what kind of energy if it starts to move, when there's motion? Kinetic energy. So we have a balance here, and we're going to see in this chapter how we're going to talk specifically about conservation of energy. But not to jump ahead too far, let's take a look at this example first. So where does the object have the highest kinetic potential energy? At the top here. So the object starts up here, maybe it bounces down, so it loses potential energy until it gets to here. It still has potential energy because it's above ground level. And then when it gets back down to the ground, it has only kinetic energy because it's moving. It's got no height. So potential energy has to do with its position, shape, or condition. So for a spring has potential energy stored in it when you compress the spring. Absolutely. Victoria, you got them all? You want her to help you? Yeah. You want to carry those over, Ms. Meyer? Thanks. Both of them. So the idea of spring potential energy is similar to gravitational, but instead of the energy being stored in the object because of its height above ground, in a spring it's stored in the coils. And we're going to see that in this section as well. Okay, so let's take a look at this example. Our formula is mgy. M is?
Mass.
G?
Gravity.
And then what about y?
Vertical distance.
Yeah, so for y, what we're going to do is we're going to look at the height of the object. Okay, the height of the object. Now, if I call this my ground level, right, if I call this ground level right here, then I could say that when the object gets here, it's got no energy. But then if it goes further down, then technically it would have like negative energy down here. So usually we call the ground itself ground level, but we could call anything ground level. We could call this the zero reference line, meaning ground level. And you could say up here there's no potential energy. So up here there's a lot, up here there's more, but then down here there'd be like negative potential energy. It's all a matter of what you call the origin or the relative or reference line. Example here. We've got an object, it's 40 kilograms. It's raised from the bottom of a well using a pulley system. So you've got a pulley and you're standing outside the well and you're pulling down on this rope. As you pull down on the rope goes around the pulley, which lifts up the object out of the well. Okay, and a lot of people used to actually get water this way before pumps were widely used. You would use a well. Now, you still use wells for a lot of things. So if people are doing some sort of like mining for minerals and stuff, they're going to have some sort of a well or a channel. They call it like a shaft now. The idea of like an elevator shaft that can go down. So its depth of the well's depth is 25 meters. The object is raised 3 meters above the rim of the well. Determine the change in the object's potential energy. So we have to think about a diagram here first. We're given the mass, right? The mass of this is 40 kilograms, so let's start with that. Vic, do you have your stylus by any chance? Let me get that. I'm just not good enough at this. It's going to get all messy. I got to find out where I put this now. So you got the mass is 40 kilograms, right? We have the depth of the actual well. So if you want to, start by drawing yourself a little well. So draw like a depth. This is the channel that the well would go down. Now here we'll call this, like right here maybe, we'll call this ground level. Okay, we'll draw the well above ground. There's the lip of the well. Okay? So the dashed line is like your ground level, really. The well itself extends above the ground. Usually a well has like a brick structure. It's cylindrical. It's sticking above the ground. And then when you look down the well, you can see a long distance. If you have no idea what I'm talking about and you've seen Batman Begins, remember when Batman's in the bottom of the well in the movie and he's afraid of the bats and stuff? That's what a well is. So you've got 25-meter depth to the well, and the object is raised 3 meters above the rim of the well. So the actual depth of the well from top to bottom is 25 meters. The object not only gets to the top of the well, but it gets raised all the way up here. All the way up to there, so that it goes an additional 3 meters above the rim of the well. That's how we have to visualize this, right? We're told that the depth of the well itself is 25 meters. We're not told that that's below ground. We're told it's the depth of the well. So it means from the top to the bottom of the well. So that's the 25 meters here. Then we have another 3 meters. And usually the way a pulley system works, a pulley system has a cable and it's anchored up top to something, and then the person is pulling down over here. And it's usually fixed at the top. Okay, so this object gets raised all the way up so that now it connects the pulley to the object right there. Okay, do we see how that works? The actual pulley is at the very top of the screen you're seeing right here. That's where the pulley mechanism is. It's not seen there. If you don't know what a pulley is, think of a wheel with very little friction, and the wheel has like an inverted shape to it so that a rope can easily pass over that shape. If you've ever done rock climbing before, and you have like a belayer is technically using an object. It's not a pulley, but it acts almost like a pulley. I have one back here so you can even see if you want to. Okay, so a pulley looks like this. Just pass this around, please. Here's your pulley itself, and there's the wheel. The rope goes over the wheel of the pulley. Okay, so this is what would be at the top there. Now, it's important that you know what these things are, okay? Because they're useful things, pulleys. They're actually extremely useful. So, we want to think about how much the change in potential energy was in this process. What was the change in potential energy? So, we're going to start from the beginning. Theo, come on. We're going to start from the beginning at the bottom of the well, and we have to get all the way to the top to where it's raised. So, how far is the change in height? What's the actual change in height we're going to utilize in this problem from beginning to end? Alejandro? 28 meters. Why, Alejandro?
Because 25 plus 3 is 28.
Yeah, clearly it's going to raise 28 meters. So when you're looking at the y value in this equation, right? When you're looking at this equation right here, the y value is again displacement. What's the displacement? It's 28 meters from beginning to end. Okay, and it's a positive 28 meters. It starts at the bottom of the well, and it goes to the top of the well. So it's going to gain energy. It's gaining energy. How? Because me or the person or you, whoever's pulling on the cable, is doing work on it. Right? Ready? Here's how it works. This is a pulley. I'm literally pulling on a rope. I'm applying a force. Look up here. I'm applying a force over a given distance. Every time I pull on that more, I'm applying that force over more and more distance. So I'm doing work on the object, and as a result, it is gaining potential energy. When you do work to help an object's motion or make it go faster or make it move in height, it gains energy. When friction does work on the object, it loses energy. Okay? So in this problem, all you need to do is go ahead and plug in. We've got 40 times 9.81 times 28 meters. Tell me what you get.
confused why 9.81
It's
is
positive.
positive.
So remember we were talking about 9.81 in the past? We were first looking at it with projectile motion, which, if we recall, acceleration had a directional down. Who asked that, by the way? Was that Ellie? Okay, because you're not looking up. I didn't know if it was you. Then the second time we looked at gravity, we considered G positive because the vector was already pointing down, correct? The thing that would make G negative, or the thing that would take into account the negative, is the directional here. So the Y is positive. Look at the Y value. You start at the bottom, and you end at the top. So you,
But wouldn't it still be negative, like 9.81?
forget, again,
Down.
stop thinking about that. Think about this. You're gaining energy from bottom to top. To go from the bottom of the well to the top, you're gaining potential energy. You're moving higher up. So you need to have a positive energy that's added. If I make G negative suddenly, what is it going to make my potential energy change? It'll make it negative. Think about it logically. You're gaining energy as you move upward. If Y is positive, right, this is positive, the mass is positive, the only way to have a positive gain in energy is for G to also be positive. Oh, this is your, I'm sorry. You want off my desk? Yeah. You got it, Frank.
10,987.2.
10,987.2?
Yep.
Agree, disagree?
I agree.
All right. I think we all agree. There's another one if you want. That's easier. Depends on, no, just so you know. So we have a positive amount of energy increasing in potential because of the fact that this object is gaining height. If it went from here down to the ground, it loses potential energy, so it would have a negative Y value, and therefore a negative amount of potential energy change. So the G is always going to be positive. It's our directional that will indicate the negative portion. Okay? All right, you could have done this in two parts. You could have done this from, ready? 25 meters up, found the energy, then another 3 meters up, found that energy, and then added those two energies together. But you would get the same answer as you do here by just using 28 instead of 25 separately, and then 3 separately. All right? Look at this example with an ant. So we were looking at an ant's potential energy. And we've got a little ant, and ants are known to be able to carry very, very heavy objects on their back. They're usually able to carry like up to 6 times their mass, which is pretty amazing. Imagine if you could carry 6 times your mass. Think about your weight. How much, if you weigh, even if you only weigh 100 pounds, so say, we range from 100 to 200 pounds, your age group maybe. Say you even weigh 100 pounds. Can any of you that weigh 100 pounds lift 600 pounds on your back? It's incredible. Some people at the gym, yes. Frankie's in a good day and one of the good workout days. But really, think about it. 6 times your weight, it's almost impossible. Okay, there's very few people that weigh 150 pounds that can lift 900 pounds. And it doesn't mean just lift, it means carry it. But bugs can, because they have exoskeletons. They have a step up on us. I mean, not in that sense, in just the structural sense. But we have a lot of steps up on them, right, neurologically? Okay? But the idea of an ant carrying its own weight. Now, let's take a look at what this says. It says that the ant's potential energy is changing because it's walking up and down hills, and it's carrying heavy piece of food, and the food varies its mass. So mass is changing, and Y, the height, is changing. At instant A, it's carrying 3.5 times its mass, in addition to its normal mass. So if it weighs 10 grams, it's carrying another 35. So together it's 45 grams, the mass. So it's carrying 3.5 times its actual mass. That's at instant A. And at this instant, it's at half the height of that at B. And at B, it's not carrying any food at all. At which of these two instances does it have more potential energy, and by what factor? So draw it. It helps you to draw. So start at a lower, so let's put the 0 reference line of here. Let's put the ground here. So it's up some hill and it's at location A. And here's the ant with some food on its back. Okay, there's the ant with food on its back at height A. The box is the ant? I don't know. So it doesn't matter, right? So it started at the ground and moved up some height. We don't know what the height is, so what should we call it? Call call it y, or question mark, which works, but let's call it y for a variable. So we'll say that this is a height of y. Now, at this instant in time, the mass of this, right, the mass of the object at A is its mass plus 3.5 times its mass. I don't know numbers here. You could plug in numbers and it will work. You could pick any numbers as long as they follow the routine here. So if I choose 10 to be the ant's mass, then it would be 10 plus 35. If I chose 20, it would be 20 plus 3.5 times 20, which is 70. But again, it has the mass of the ant plus the food. This is the ant itself, and this is the food. Then it continues to a height B, and we're told that A is half the height of B. We're told that at instant A, it has half the height that it does at instant B. So let's go up a little higher. And let's make instant B up here. What's the height at instant B? What's the height? In terms of some variable that we already know. Alejandro?
No, I don't know.
Something you're asking? Stretch. Again, read, guys, read. Come on. It says, ready? At instant A, it's carrying 3.5 times its mass in addition to its normal mass, and it is at half the height of that at instant B. So this is half of the entire height. So what's the entire height?
Y2?
2y.
2y.
Yeah, y times 2. The height at instant B is twice that of instant A, so just call it 2y. You could pick a height, I don't care. Pick 5 for y, then 2y is 10. Pick 20 for y, then 2y is 40, etc., etc., etc. The goal is to figure out which instant the ant has more potential energy. At one instant, it's lower, right? But it's got a lot more mass. At the other instant, it's higher up, but it dropped the food along the way. Unfortunately, this ant couldn't carry the food, and the mass at this instant, B, is just the mass of the ant itself. There's no food involved there. Remember, it's carrying food, so it's got all this mass to it. Then it goes up to level B, where it drops the food. So now the mass is only simply M. Okay, only simply M. So go ahead, think for a moment, how would you find out the potential energy? It's going to be all variables, right? So the potential energy at instant, let's start with instant A. What's the mass when it's at height A, or instant A? What's the mass? Remember, it's the ant and the food at instant A. What would the mass be? What's M plus 3.5 M? Ant?
4.5?
Right? Ant. So it's 4.5 M. That's the mass right there. G is G. And the height at instant A is known as Y. Remember, potential energy is mass times gravity times the height. Okay, it went from the ground up to height Y. That's the height right here at instant A. What about at instant B? What's the mass when it gets to the top of this plateau or this little hill? Theo, focus. What's the mass when it gets to the very top there? Yeah, it's just its own mass, M. Remember, the first time it had the M plus 3.5 M for the food, giving it 4.5 M. But it dropped the food went falling down the hill, and the ant safely made it to the top, thank God. And it's just the M at the top now. Now, we know G is still G, it's still on Earth. What's the height at the top?
2y.
2y. So although we know no numbers, we can still evaluate everything in terms of variables. So 4.5 times M times G times Y is just 4.5 mgy. It's all in variables. So we're going to look at the coefficient, is what's important. And the second one is M times G times 2y, that's just 2 mgy. So which one, just look, you don't need numbers. Which one has more energy? Does it have more potential energy when it has more mass and less height, as in instant A? Or does it have more potential energy when it has less mass but more height, as seen in instant B. Which of these is a bigger number? Clearly A. Now, the second part of the question is by what factor? How do you get from 2 to 4.5? And don't give me a number that you would add to it. That's not a factor. That's an addend. 2 times what number gives me 4.5? 2.25. And Theo could also do that. I'm sure he probably just did. He just divided 4.5 by 2. Okay? Or anyway, you might have done it, right? But to find the factor of increase, take the larger answer you have. Right, here's the larger answer. Over the smaller answer, this will give you the factor of increase. This works for all things, not just physics. If you want to find a factor of increase, take the larger divided by the smaller. What happens to the MGYs? So you just simply have, as Theo told us, 2.25. So when this ant is at a lower height, it actually has more potential energy in this problem because it has more mass. So the increase of mass having that food had more of an effect than simply increasing the height and dropping off that mass along the way. Okay? We can finish this section. We might go over by like 30 seconds or a minute, but just bear with me, okay? We're going to do our last example here. All right. So to store it in a spring, another formula, another one you don't have to memorize, okay, but you need to know what things are. What is PE probably again? Why did I put a little S there? Spring or stored? I call it spring. Some books will write PES for stored energy, but no matter what, if you have potential energy, it's stored. So I call it spring, PES for spring. 1/2 kx squared. Now this is the energy associated with a spring either being stretched, and it wants to come back, or compressed, and it wants to expand. And you can see this, and it's not obvious unless you have a pen that you can remove the spring from. I can't remove the spring from this. Some pens, when you open up the pen, the little spring comes out, and when you press the spring together, if you let go, what happened? It might like spring off. Spring, like a spring, it shoots off or something. That's what's called the spring. The spring's back. So here, the K value, you should jot this down, is called a spring constant. K is a spring constant. It's a material property, like density. Okay? It's a material property of an object. It has to do with many parameters that really don't matter, but it has to do with the length of the spring, the material of the spring itself, the cross-section. There's a bunch of stuff that involves the spring's actual K value. But I'm going to give you the K value. It's called a lumped parameter because it's based on several things. So I might give you a spring, or in your lab, what you're going to do is actually calculate the K values of some actual springs by seeing how far they stretch under a given force that's applied. Okay, so we're going to see how that's going to work with Hooke's law a little bit later. X. So by the way, K is spring constant. Another word for it? Some books call it the spring stiffness or the spring's rigidity. So a spring that is very difficult to push down, a very strong spring has a very high K value. The spring from your pen has a very low K value. And it makes sense. It's directly related to energy. If it's a really strong spring and you compress it, it gains a lot of energy. There's a lot of stored energy in there. But if it's a really weak spring and you compress it, you're not really giving it too much energy, okay? X is the change in the spring's length. X is the change in the spring's length. It's not displacement. I mean, technically speaking, that's what displacement is, a change in length. Okay, but don't get confused with the word displacement though here. Think of X as the change in the spring's actual length. All right? Now, the units on K are going to be newtons per meter. The units of 1/2 are nothing. The units of displacement or change in length are meters, and that's squared. So take a look. You end up with newtons times meters squared over meters, which in reality is just Newton times meter. And a Newton times meter from our first lesson on work was a joule. So again, the units are joules. Not a coincidence. It's energy, so the units have to be joules. Let's see an example of this now. Okay, so our units match up is what I'm getting at there. We still get back to joules because Newton times a meter is a joule. So we've got compressed from its free length. What do you think free length means? Yeah, when the spring is sitting there on the table, give me, again, 30 seconds to a minute, please. We'll get through this. Okay? You compress the spring by a certain distance. You're told you compress it. Shh, listen, we'll get quicker if you sit for another second. We go from 10 centimeters to 4 centimeters. What's the change in length?
6.
There we go. The change in length is 6 centimeters, which is really 0.06 meters. The K value, or the rigidity, look, the rigidity of the spring is represented by a stiffness of 300 newtons per meter. And we want to find out how much potential energy is stored in the spring. We can simply plug in 1/2 times K times X squared. That will give us the potential energy in the spring of 0.54 joules. Okay, it's a certain amount of energy stored in an actual spring. Your homework, again, the rest of this 5-2, you could have started last night. Okay, but finish this up, please.